Hi, my name is John, and today I will be presenting on our research on biogenic synthesis of nanosilica for nanofluid applications. Nanofluids are fluids that contain nanoparticles which significantly enhance heat transfer. Silica nanoparticles are commonly used in this fluid, but their conventional production involves expensive and toxic chemicals. We propose a more sustainable method that extracts silica from biomass, such as rice husk and sugarcane bagasse. This eco-friendly approach can produce nanofluids with improved thermal property, making it a promising alternative for future applications. Our research addresses several key issues. First is unsustainable practices. Traditional nanosilica synthesis relies on hazardous chemical and energy-intensive processes, necessitating a shift toward greener methods. Second is biomass availability. By utilizing biomass as a valuable resource rather than waste, we can use renewable agriculture waste like sugarcane bagasse as a sustainable feedstock for scalable nanosilica production. Third is research gap. Conventional nanosilica synthesis use petrochemical-based precursors like tetraethyl orthosilicate. However, sugarcane-derived silica are underutilized, with field study exploring its potential for nanoparticle synthesis and nanofluid applications. Our study has three main objectives. First is to investigate and compare different biogenic synthesis methods for producing nanosilica. Second is to study the effect of various nanosilica concentrations in nanofluids. Third is to evaluate the potential of biogenic nanosilica-based nanofluids in industrial applications. For the methodology, nanosilica was synthesized using Soldier method. First, the sugarcane bagasse was chopped into small pieces after being cleaned and dried. Sugarcane bagasse was calcinated for 2 hours at 650 degrees Celsius. 1 molar of HCl was used to leach sugarcane bagasse ash by the ratio of 10 HCl to 1 ash. Then the mixture was continuously aerated for 1 hour at 100 degrees Celsius. The residue underwent several washes with distilled water. After the leached sugarcane bagasse ash mixture was being filtered. 1 molar of NaOH was added to the wash residue in the ratio of 8 NaOH to 1 residue. The mixture was then continuously aerated for 1 hour at 100 degrees Celsius. Sodium silicate was the filter obtained from the filtered mixture. For the gelling procedure, the solution was saturated with 1 molar of HCl until pH 7 was achieved and alcohol was created. It was opened for 1 hour at 60 degrees Celsius. The powdered gel made of synthetic silica was ground in agitated mortar to produce silica nanoparticles of uniform size. The resulting silica nanoparticles were sorted using 200 mesh screen. Following by nanofluid, two-step method is being utilized to synthesize nanofluid. In this method, nanosilica was firstly prepared using Soldier method. After that, nanosilica in the concentration ranging 0.05 to 0.2 weightage percentage was added to Chinese ink distilled water solution to produce nanofluid. Chinese ink was chosen as surfactant because carbon black particles and animal glue, which is collagen, are present in the Chinese ink. This allowed Chinese ink function as an effective surfactant to improve nanoparticle stability in base fluid. The distilled water acted as base fluid for the suspension. Then the nanofluid was dispersed using ultrasonic bath for 20 minutes to break down the agglomeration of nanoparticles. The FTIR analysis showed the presence of SiO as ice-stretching vibration band at wave number of 1000 to 1100 cm to the power of -1. This confirmed the successful extraction of silica from sugarcane bagasse. The SEM result provide insight into the morphology and distribution of the synthesized nanosilica. At low magnification, the particles appeared clustered with visible agglomeration. At higher magnification, we observe individual particles and rough surfaces, indicating high reactivity and porosity. For zeta potential, blank has the value of -23.7 MV. For 0.05 weightage percentage, has the value of -21.4 MV. For 0.1 weightage percentage, has the value of -17.5 MV. For 0.15 weightage percentage, has the value of -17.6 MV. And lastly, for 0.2 weightage percentage, has the value of -15.5 MV. So lower concentration of nanosilica provide better stability, while higher concentration reduce stability due to the decreased electrostatic repulsion. For UEV's result, it shows that lower concentration of nanosilica result in better stability and dispersion, while higher concentration lead to aggregation and sedimentation. For viscosity, as the concentration of nanosilica increase, viscosity of nanofluid also increase. For pH value, as the concentration of nanosilica increased, pH value also increased. In conclusion, lower concentration of nanosilica were found to be more stable and suitable for practical application requiring long-term stability. Our study highlights the potential of using biogenic nanosilica in industrial application where stable colloidal suspension are essential. This is all for me. Thank you.